Okay, I'm going to, it's good to see the theorists showing the nuts and bolts and gears, what they're doing, because this is an experimental talk in which I am going to get into some detail. Okay, so I want to talk about all sky spectrum measurements of the 21 centimeter line, the bottom curve of the logo of the conference here, the measurement of this global signal, sky glow signal of the 21 centimeter line, and I personally have begun to realize, maybe a little later than some, how critically important it is to measure that global signal in addition to the imaging experiments, the three-dimensional imaging experiments, LOFAR and the others, that will map structure. Knowing what the background thermal physics is doing is absolutely essential to understanding what's going on. So I think it's absolutely critical to measure this curve in addition to doing the imaging experiments. And to me, it's just as important information and essential. It's very hard to do, of course, because the galaxy foreground is 1,000 Kelvin at those frequencies, and you have to subtract it out to see that global sky glow. So it's a very important measurement that is very difficult. And that means to me that there ought to be several groups doing this, and they ought to have techniques that differ in their systematics. We need several efforts here to do this properly. If two completely different experiments, different teams, get the same result, then we can believe it. Okay, so I have two approaches to talk about today, and I've made some progress in the lab on the first one, and I've done nothing on the second one. The first one involves using a black body calibrator to do this experiment. As far as I know, no one has tried this yet. We've done some tests in the lab to see if we think this will work. Now, this is how the FIRAS experiment got its beautiful result. FIRAS, the wonderful FIRAS spectrum, Nobel Prize winning spectrum of the CMB Planck curve that instrument works so beautifully because it has an external calibrator that replaces the sky that is black to probably 6 nines black. Absolutely black calibrator held at 2.7 Kelvin, replaces the sky, and they measure indifference to that. And so this is what I'm suggesting for the 21 centimeter experiments, to use a black body that replaces the sky. If we do this, I'm going to talk about how these black bodies work. I myself did a CMB spectrum experiment in the 80s before FIRAS, not nearly as good, of course. And we developed black body calibrators for that are very similar to the ones on COBE. So I'm going to talk about how to do that. And if you're doing this, you design the black body first, and then you design the antenna to work as well as it can with that black body. Black bodies are not perfect, and there are ways to optimize the antenna so they use the black body well. So that's the approach I'm taking, number one. Number two involves using an interferometer to measure the total power. So I'll get to that later. The interferometer will be used in a beamforming mode, a digital beamforming mode, meanwhile calibrating as an interferometer at the same time. So that's the idea I'm thinking about there. And I have a little data for each of these just to show you. It's interesting, I hope. Okay, so here's what I'm thinking about for this black body calibrated experiment. We would have corrugated horn antennas. These work very well, and I have measurements to show you how well they work. However, they don't have quite the bandwidth of this 4-point antenna that Edges is using, or the fat dipoles that Ravi Subramanian has developed at RRI. So those are full octave antennas, or maybe a little more, and these are really half octave antennas. So you're going to want several of them scaled in size, scaled copies of each other. And then I'm imagining there are rails that carry black bodies over these instruments to calibrate them. And you want black bodies of two temperatures, so you do a hot and cold load calibration. Okay, so first the black body. How can you make a black body that's black? One of the, I think probably, as far as I know, the best way to do this is to make a conical shape. Okay, this is very helpful, and I'm actually going to make one for you. So, I have a black material here, and you can see it's black, but it's not perfectly black, right? Because you can see it, right? It's not perfectly black, right? I can sort of show you how black it is. We can do the famous blackness sort of experiment, which is you shine a light on it, you see how much comes back. So let me just use my little laser pointer here. So that's the black stuff, and here's white stuff, right? So how many magnitudes difference is that, you optical astronomers? How black is this stuff? You know, it's I don't know. Is that 3 magnitudes? It's at least 3, I think. Huh? So that makes this few percent. The albedo is a few percent. This is scattered light. At 100 megahertz wavelengths, a planar sheet has a specular reflection almost entirely. It doesn't really scatter. The edges scatter by diffraction, but the planar surface, all the structure is sub-wavelength, and so that reflection is specular. So you have specular reflections, and now you can make this material. This material is probably 3%. 97% black. However, I can make it much blacker here. So I'm going to make this much blacker. And here we're going to go making it blacker. All I have to do is roll it into a cone. Now, you probably have looked down a railroad tunnel at some time in your life. That's black, right? Look down a railroad tunnel. It's extremely black. So here's a railroad tunnel for you, right, that you get to look down now. So is that black? Okay. This is how you make it black. And if you're thinking, this is mostly diffuse scattering in the optical, and it's specular scattering in the radio. So let's think about specular scattering in a cone. Let me take a paraaxial ray and shine it into one of these tall cones like this, right? Well, it has to bounce quite a few times before it can come back out again, right? So here it is, it bounces, but it goes deeper into the cone, right? It's deflected more across the optic axis, central axis here. But it has to bounce this one 7 times before it comes back out again. So now suppose that I have material that's 3% black, or 97% black, only 3% power going onward. So I have 3% of the signal here, send in my laser beam, right? 3% here, then 3% of that, then 3% of that, so on, right? So I have 0.03 to the 7th power. That's black. Okay? So this is how you make a black body. Well, it's very black for paraaxial rays. It's not so black for oblique rays. Okay? An oblique ray, if I have some antenna down here I'm trying to calibrate, if the antenna's got a large angle response, that's going to see the side of this cone. Now you can change the geometry. I can make a teardrop shaped thing that comes in like this and try to make sure there's no face ever looking back at the antenna. You can do things like that. But if you're just using a straight cone like this, you want to avoid a bit more than with the current antennas, a large angle response. Okay, so the antenna should be made to match the black body. Okay, now I want to talk about how to make the material black. So this paper is black because carbon black has been soaked up in the paper, and that's why it's black. It's black because it's conductive, basically, at optical frequencies. What? Yes, that's right. This is there's some of this for sale in the flea market in Pakistan. So So here is how you make stealth material. Now, everybody, this is secret, so don't tell anybody how. So here's the familiar Fresnel relation that you all know. You probably worked this out for yourself when you're an undergraduate in your E&M class. So we have a wave coming in, hits a planar surface, and you do the E and B boundary conditions and so on. So now, if this is a material that has a dielectric constant but is not magnetic, then we can express the reflection coefficient using the index of refraction, square root of mu epsilon. And this is the Fresnel amplitude reflection coefficient that you're all used to, n minus 1 over n plus 1. That's the 4% power reflection of my glasses, right? Index 1.4 gives you 4% when you plug it into that. And you square it to get 4%. Okay. Now, if you have magnetic material, this is not the correct formula. You need to match E and B. if you have magnetic material where mu is greater than 1, epsilon is greater than 1, and mu is greater than 1, you need a second parameter to describe it. The index is the wave speed, but you also need a wave impedance, and that's the ratio of E to B, right? So, the wave impedance is mu over epsilon square root, and now the correct formula is z 1 over z minus 1 over 1 over z plus 1. Okay, which means that I need to divide the n by mu, and mu was 1. So this formula is correct, and this formula is also correct. However, I now have the opportunity to make z equal to 1. And how do I do it? I mix in enough magnetic stuff into my plastic so mu matches epsilon. I've now matched the wave impedance to 1. It's 377 ohms per square wave impedance. And the wave now does not reflect. And this is how an F117 gets a 1 centimeter squared cross section. Okay, so, and that's how they do it. So you can make material at radio frequencies that is exquisitely black to begin with on just one bounce. Not enough to you can calibrate the experiment with a plain sheet. You still need to make the cone. Here we go. So, so can you buy this stuff? Sure, you can buy it. You can buy these tiles from TDK. They look like bathroom tiles, 4 inches square and 6 millimeters thick. And this is the reflection coefficient face on of one of these squares. Okay, and here it is. Over this whole, and this is the frequency range we care about, like 50 to 200 here. This is where all that action is in the spectrum, right? And so how good is it? Well, so this is the place where mu matches epsilon, right? And the magnetic's losing its magnetic properties as you go up in frequency. The magnetic domains can't respond very fast, and so mu is falling with frequency. Epsilon's fairly flat. But anyway, they match right here, and it's 4 nines black, 40 dB down reflection, 4 nines black all by itself on one reflection. 4 nines black. Wow, that's impressive, right? And it's even better than 1% black. 99% black over this whole frequency range. That's normal incidence. Grazing incidence reflections go up. It's not quite as good at grazing incidence. That's true of everything. Almost everything is shiny if you look at it. You take a flat white piece of paper and you look at it. Grazing incidence, you can see reflections off of it. Okay, so that's the material you can use, and then you don't need to be so tall with your cone. Your cone can be a little shorter, but you still want to avoid those oblique angles in the antenna pattern. So what kind of antenna might you use? And I've said we would maybe use a corrugated antenna, horn antenna for this. So this is the corrugated horn antenna I've been thinking about. So we've been thinking about putting an array of feed horns on the Green Bank telescope, and it turns out that the Green Bank telescope is a scale model of a satellite dish. It's exactly the same F number, so it's just a big DirecTV dish out there in West Virginia, right? And what we want to do is we have now one feed horn on there at 800 megahertz to do the Redshift 1 stuff. There's a poster on it that you can take a look at, what we're doing at Green Bank. We want to put multiple feed horns on there to map faster. And so we've been looking at this feed horn, and I found this is made by Weingart, and I found the patent for this feed horn, and this is from their patent. Okay, so this is what they put there, Weingart. It's a circular wave guide, a little bit of a conical horn, and then 3 little quarter wavelength choke grooves on a conical shape. So this is a different cone. Okay, so that's how they made their. There's hundreds of years of engineering in this stuff. It's refined to the nth degree, right? And this is the pattern. Look at that. Isn't that a beautiful pattern? I mean, here's 90 degrees, plus and minus 90 degrees. No side lobes whatsoever to this thing. Beautiful Gaussian for most of where the power is, a little bit extending beyond a Gaussian, but no side lobes whatsoever. That's a beautiful pattern. So I said, okay, well, we're going to try this. And I've made now 3 of these things, various scaled models. I ended up cutting off the outside groove. I didn't think that helped me much, and I got rid of this cone in the middle. Eventually, I mean, like I said, I made 3 different versions of this thing to test in the lab. But here's the one we tested on the antenna range, and this is real rough, and I just made it in an afternoon in the shop out of sheet metal and this electric field probe. This is a little bit of sliding tube here. I can tune the length of that probe. There are much better transitions than that one. That's kind of a poor man's E-field probe, but it's good enough for a first test here. So we have an antenna range at CMU, and it's used to test Wi-Fi antennas at 2 gigahertz. So I had to make a copy of this thing for 2 gigahertz. And here are antenna patterns. These are now measured antenna patterns. The question was, so Weingart designed this for 12 gigahertz. Does it have a wide bandwidth? Well, here's the answer. Sure enough, it does have a wide bandwidth. So here's 1.7 to 2.5 gigahertz, and here's this beautiful antenna pattern now, polar plot of that same antenna pattern. And it's changing a little bit with frequency, but gosh, so the 3 dB point is right here, right? So this is the main beam here. It's like about a 40-degree main beam, like that. And then all this other stuff is really falling very fast. It's going down to 30 or 35 dB here. All right? So it's going to look into the cone with an angle like that. Okay. This is the H plane, and the E plane it's doesn't have quite the bandwidth. So here's the good part of the E plane. Here's the not so good part of the E plane. So E plane is the direction that the electric field probe is. So the electric field probe is like that, and this is in that plane. And you see what happens is when I go to the highest frequencies, I'm getting a non-symmetric pattern. And that's probably because I'm exciting the next circular waveguide mode with that probe. And if I made a symmetric probe, and maybe probe 2 sides differentially, I think I might be able to get rid of that. And also, I have not tested this down to the waveguide cutoff. It probably is still working down to 1.4 gigahertz, but our antenna range doesn't go down there. So basically, it's a half-octave antenna with a beautiful antenna, beautiful pattern over a half-octave, and a bit narrower beam. That's Florence, the senior who did all this work. Just now graduated, and there is our black body. I think I got a better picture of it. This is Edgar. I didn't get a picture of him from the front. But Edgar's coming to be a postdoc in my lab on Friday, so that's exciting. So he's going to work on this. Here's this black body we made. So we also tested a black body. Now we didn't have any of these tiles. We just had some of the stuff that the anechoic chamber was made out of. So this is actually grooved material. And we've taken 2 pieces of grooved material and interleaved them like this and make kind of a teepee out of that. And it's not 4-sided, it's only got 2 sides. But the idea is if that structure is reflecting, we're in trouble. Right? So we put that on top of our horn and moved it up and down to see if we could see standing waves. Okay? So that's a reflection test of that black body. Is it black? It's like shining the light on the paper. Can you see anything coming back? So we transmit with the horn and we see if we can see anything coming back. And we can't see anything coming back, but our measurement's not perfectly sensitive. So here's the test. And we do move it up and down. We change these shims here, 1-inch spacers. We gradually bring it up and down and make the measurement over and over again. Try to see if we can see anything changing when you move it up and down. But the uncertainty of our measurement, we don't see any signal. The uncertainty of the measurement is 40 to 50 dB. This is not the optimum material. It's just our first try. And 40 to 50 dB. And this is not this tuned material, right? That has 40 dB on 1 bounce. Okay? Okay, so I'm very encouraged here. So here are the conclusions of the approach number 1. The scalar feed does have a clean symmetric beam pattern with a bit narrower bandwidth than beam width than the dipole type antennas, and it has at least square root 2 bandwidth. So that's pretty good. I think that's a viable antenna to use for this. Black body reflections are measured at less than 40 dB, demonstrated at 2 gigahertz with non-optimal material. My guess is we probably can get down to about minus 70 dB if we try here. So minus 70 dB really cracks this problem. That means you can make millikelvin calibrations. You can measure you're going to measure the absolute flux from the sky at the millikelvin level. You still have to subtract out the galaxy, which is 1,000 Kelvin, and leave a 10th Kelvin signal. But so that's still. It's going to be made perhaps a bit easier if you can do this very well calibrated radiometry. Okay, now here's approach number 2. And we haven't built anything for this, but this involves making an array, an aperture array. So can I do better than this antenna, this corrugated antenna? How about this? let's make a very densely sampled aperture array lambda by 4 sampling, okay? Sub-Nyquist sampling, so that even over a range factor of 2 in frequency, it's still sub-Nyquist, okay? And then I'm going to sample all the signals, 256 times 2 signals here, and then I'm going to create a profile, a sensitivity profile across this aperture by putting in the right coefficients, a cosine squared function, apodization function. When it goes to 0, I keep it at 0, okay? And then I let the width of that vary in proportion to the wavelength. Okay? Now the beam pattern will be independent of frequency. Okay? I can make a beam pattern. It'll have a very nice clean beam. The beam pattern can be independent of frequency. This is Max will love this because he's hoping to make one of these out of MIT tiles, and if you use it at a longer frequency, it'll be this thing, a longer wavelength. Okay. Okay, so there's our beam. You make the beam by summing in the computer. You make this beam. Now, meanwhile, you can use this as an interferometer. You can, for every pair of dipoles, get the fringes that come from the bright sources that are moving constantly across the sky as the Earth turns. Okay? So what's that good for? Well, you know that these sources have a very smooth synchrotron spectrum. And so you could, by making measurements over a wide range of frequencies and assuming a power law fit across the frequency range of interest, you can calibrate them versus frequency. And that means you can calibrate what the gain for signals from the sky is of each of these antennas. And that means you can calibrate the summing lobe that you're putting on the sky. Okay? Okay, so you're calibrating this using now not black body, but radio sources on the sky. You still might want to try a black body. I haven't figured out exactly how this will work, but you could. It's now going to be an even bigger black body. You can't probably use a cone. You need to kind of corrugate the cone. But you could still put a black body over it if you want to. And that might be useful for determining the amount of noise that's coming from your amplifiers. You have no way of measuring the noise that's coming from the amplifiers using the interferometric calibration. You have to assume that it's flat with frequency. Usually it is very flat with frequency. In the real amplifiers that I've tested in the lab, it's amazingly flat. But it would be embarrassing if there was some spike in your noise spectrum that you wrongly interpreted as flux from the sky. Okay, so there's that scheme, and I haven't really built anything. But we have tried to do something like this experiment using our Pittsburgh cylinder telescope. So we've built this telescope. It's a prototype for a dark energy test, a baryon oscillation dark energy test, using cylindrical reflectors. In 1D, it's an FFT telescope. In the other dimension, it's just a reflector. And so we've built this. So this is kind of one-dimensional version of the thing I'm talking about. So we can try this idea on it. So I'm going to show you that. So here are our little dipoles. So now we only have them in one dimension, and we use the reflector to get some selection on the sky in the other direction. So these are X and Y dipoles on circuit board here. You can see, and the amplifiers right there on the circuit board. Right. Yeah, there's a picture of the antenna cards. And here are some real calibrations using the famous radio sources of the sky. And this is one dipole with another dipole someplace in the array. And here's the interference pattern that comes from Cygnus A. Okay, so there it is. So these are the fringes. That's telling you what each of those antenna gains is, the product of them. But of course, you have all products as you do the correlation matrix. So it's pretty well measured, and the gain is stable from day to day. Here's gain on the 24th and the 23rd measured with Cas A. And these are visibility-based gains. You can do an antenna-based gain calibration as well. Okay, so that's all working. And now, can we measure the spectrum? Can we see the 21 centimeter line, having measured the gain of all the antennas? There's the 21 centimeter line. This is the Milky Way. This is the glow of the Milky Way, measured with one antenna. It's been calibrated by measuring all of those cross-product visibilities. Now, this is a big signal. This is 15 Kelvin. Each of these dipoles makes a stripe on the sky that's 2 degrees by 90 degrees. That's crossed by the galactic plane somewhere. Gives about a 15 Kelvin 21 centimeter signal. If you look right into the plane, you get over 100 Kelvin, but our beam is diluted. The galaxy only crosses a piece of our very elongated beam from one dipole. Anyway, that's a 15 Kelvin signal. Of course, we're looking for 10th Kelvin or millikelvin level signals from cosmology, and they're much broader, right? This is 10 to the minus 4 width. So there was the question, could you see a 100 megahertz splitting of the 21 centimeter line? Just today. Well, probably. If that line were split as a 100 megahertz doublet, I think I probably could distinguish that from that shape, maybe. You really would like a bit narrower velocity width than that to really separate a 100 megahertz doublet. But anyway, yes, you can measure the line. Okay, I'm almost done here. We're thinking about doing this in Mexico. I have Mexican colleagues working on this, and they want me to try this Isla Guadalupe as a place to do this. So it's 250 kilometers from Ensenada. That's probably the brightest source nearby, and San Diego's right above it, right? So that's where a lot of the RFI is going to come from. It's quite a ways from there. And also it's got this tall mountain range in it. The island is 4,000 feet high, and so you can sit over here maybe on the little bit of flat area that this island's got. It's not a very nice place, but Mexico wants to keep it because it extends their oil rights out here 200 more kilometers beyond that. So this is worth probably $1 trillion to Mexico, that little island. So anyway, they'd love to have us there and have more activity on the island. So we're going there next month to see how quiet it is. It's not a friendly place. You can see it's. That's the south end of it. But it is quite tall, so it will provide some additional shielding of meteor scatter from the mainland. Okay, so conclusions. I think it may be possible to get below the millikelvin level in the calibration of these global experiments, if we try. Conical black body might be a good way to do that. I think there should be multiple experiments. I have a tremendous respect for the EDGES experiment. It's a brilliant experiment, and I love it. But I think we should have more than one, and they should be different from each other so the systematics are varied, and hopefully we'll see the same signal with more than one experiment so we can really believe it. That's it. Yeah. Entertaining talk.
Very exciting stuff. But I have a question about the black body idea here. Since the synchrotron doesn't want to add a black body at all, are you planning on adjusting the temperature of the cone as you write this?
Well, I think for each range of frequencies, you're probably better off leaving the temperature of the black body stable. It's going to be big, it's 20 feet across, right, and 30 feet tall. This cone that I'm talking about, it's a $50,000 worth of RF absorber, and it's just kind of ceramic, sintered ceramic material, and then there's some metal case around it that you're heating or cooling to keep the thing hot or cold. You can't really move it around in temperature too much. So I would have two at different temperatures. That's probably the best you can do. And then you have to extrapolate to the real flux you're seeing, which will be, at low frequencies, much greater than the hottest one. Yeah.
Okay, so you're not going to try to exactly null it?
You're not going to null the signal as Fire-S did. Yeah. Yeah, the guys at Brigham. So does mutual coupling between the antennas affect the performance of the array? That's basically your question. It probably will be important, particularly if they're lambda by 4 apart and not each resonant. So it probably will be important. The people who've thought most about this is the feed group at Brigham Young, And they've actually measured some arrays, the mutual couplings in arrays for aperture plane synthesis arrays to go on telescopes. So they're building something for the Green Bank telescope that's got an array of dipoles, and they've measured the noise couplings between the dipoles. I haven't gotten far enough in my thinking to figure out how big a problem it is, but I'm sure you'll have to consider it. Yeah. Chuck.
So your approach to it looks a lot like that LWA station.
Well, it's regular and oversampled, but it does look a lot like the LWA station. Yeah. What do you know about that?
Well, we propose to do a very similar thing.
That'd be great. Yeah. Yeah. Yeah.
Any other questions?
Especially with
So the moon is a fairly close match to the temperature of the sky, right? So there's not that much contrast off the moon. The moon is roughly 300 Kelvin. The sky is roughly 300 Kelvin. So as the moon moves through various parts of the galaxy, you can see it. If for the DARE experiment, which would be at the moon, you could point the whole thing into the moon, and I think that would be an interesting method of calibrating DARE. Then it's a full beam calibrator. Of course, it's not black. The moon has sort of a 10%-ish reflection. Yeah, but it probably can be modeled. I think it's probably a very good way to calibrate DARE.